Hello everybody, I think it's time. Welcome back to another episode. Um, we are talking about convergence of sequences of functions, right? Um, just just to, I feel like I should say something because the class is almost over, but I don't really have much to say. We're going to have a final exam next week on Friday. I will set aside some time to review for the final, but otherwise we're just going to keep on pressing on. Anybody have any questions about logistics for the rest of our time together? I don't think there's much to be said about it.
The final is cumulative?
Yes, yeah, this is something I should say. The final, my intention is to make about half of it based on the new stuff that is since the previous exam we took, and then the other half is kind of anything goes, so it will be cumulative. We'll talk more about that next week, I'm sure. Anything else? All right, great. Let's get to it then. Actually, we're going to finish talking about sequences of functions today and move on to something completely different. What we talked at length last time about was about pointwise convergence versus uniform convergence. The example, this is sort of the first example we talked about, is e to the nx. Remember that one? If you look at it on the left side, these functions look like this. They all go through this point. They have different steepiness. And what they converge to pointwise is this function, which is constantly 0 here, plus this one extra point. And that is not continuous. So the moral of the story for this one is Fn, I'll say if Fn are all continuous and Fn converges to F pointwise, I'm going to say still F may be discontinuous. Right? But this, and I mentioned this last time, but we didn't actually discuss it in detail. This cannot occur if the word pointwise is replaced by uniform. So it is a theorem that we're going to talk about that if they converge uniformly, then the resulting function must be continuous. If you have a bunch of continuous functions and they converge uniformly to something else, then the something else they converge to must also be continuous. All right, let's see if we can do that. Actually, the proof of this is not so difficult. When you see the basic idea, you can sort of look at the picture and get the basic idea of it. So here's the theorem. If Fn are continuous and Fn converges to F uniformly on some set on A, then F is continuous on A. I meant continuous on A for all of these things, right? They have to be continuous on the same set, that they converge uniformly on. All right? If they're continuous on A and they converge uniformly on A, then the thing they converge to is continuous. So the idea, I'm going to try and draw a picture which will inspire the proof that we're going to use. Let's say that I have my functions. Let's say the blue one is the thing that they converge to, and the red functions are the things which are going to converge to the blue one. So maybe they go, and let's say A is like this set over here. This is the region in which they converge uniformly. What that means is eventually the red line, all the values along the red line are within some kind of epsilon neighborhood of the blue line. All right? So they're converging that way. The red ones are getting super close to the blue one. This is the picture you should have in mind for uniform convergence. Now, can we demonstrate that the blue one is continuous? For that, you need to show that if, you know, it's a thing with the epsilon. Maybe I'll start by saying that. I'm going to say, so here's my proof. I'll start the proof. I want to show that f is continuous, right, on A. And in order to do that, you have to, first of all, show that it is continuous for every point of A. So I'm going to say pick some particular value C in A, and then I want to show f is continuous at C. And how do you show a function is continuous at a point? You do the whole epsilon thing. So I'm going to say let epsilon greater than 0 be given. I wrote be given like one word. Let epsilon greater than 0 be given. We'll find delta greater than 0 such that x minus c less than delta, I gotta put a 0 there, implies f of x minus f of c less than epsilon. Alright, this is what we have to do. What we have to prove has nothing to do with fn, right, the sequence of functions, but you're somehow going to use the sequence to demonstrate this. And here's the idea. I said you could describe the idea fairly easily on the picture. Here's the idea. We have, my 2 points are x and c, and we imagine that they're pretty close together. Let's say x is there and c is there. And what we have to discuss is f of x and f of c. Those are the values on the blue curve, right? That's f of x and f of c. And I want to show that those two values are close together within epsilon. And it's, I don't know if they don't look super close on this picture, but we're talking about their y values are close together. Actually, their y values are quite close together on this picture. But anyway, how we're going to demonstrate that is the fact that this is actually going to use an epsilon over 3 trick with the triangle inequality in 3 separate points. Check it out. We start with f of c. We want to show f of c is close to f of x, but because of the convergence, f of c is really close to fn of c, right? This distance is going to be very small because they converge, the fn's converge to the f. And then also this distance over here, fn of x, is going to be close to f of x. And then the distance here is close because fn is continuous. So we have sort of three different little differences which we're going to make each of those 3 distances smaller than epsilon over 3 in order so that it all adds up to being smaller than epsilon. This is the idea. You'll see how it works out. The proof is actually fairly straightforward to write if you have that basic concept. I hope that you can still see. I just shrinked it down quite a bit. But my sort of work on the side that I usually would do in an epsilon and delta proof, I'm going to break up f of x, sorry, I'm not going to put it in a bracket because I want to say some things. I'm going to say let n be a natural number such that n greater than n implies fn of x minus fn of, sorry, minus f of x less than epsilon over 3. And fn of c minus f of c less than epsilon over 3. All right? This is possible because fn converges to f uniformly. And the uniform is important. It means you can use the same n for both of those points, the x and the c. They use the same n. They don't have to use 2 different n's. That's where the uniformity, uniform continuous comes in. All right? So if n is bigger than this n, then the fn of x minus f of x. Sorry, I messed this up. Not a lot. These big n's here, I meant little n's. That's because that's what uniform, or that's what the convergence means. When the little n is bigger than the big N, then the f's are close to, the fn's are close to the f. All right. This takes care of like the 2 sort of vertical lines here, right? Those will each be less than epsilon over 3 because of what I just said. And then how can we make that sort of more horizontally one? also less than epsilon over 3, I can say so I should just say this is possible since Fn converges to Fn converges to F uniformly. Fn converges to F means the Fn's get very close to the F, like within epsilon over 3. And the fact that it's uniform means I can use the same n for both. All right. And since F is continuous, not F, Fn is continuous, this means that there is some delta such that x minus c less than delta implies Fn of x minus Fn of c less than epsilon over 3. All right? Because of the continuity, we can make Fnx minus Fn of c less than anything, and in particular, I'm going to make it less than epsilon over 3 so that I can add it up those other things. All right? Now we have all the ingredients are kind of set up here to do this big old epsilon over 3 trick. So I can say then, like we have chosen this delta here, so then if x minus c less than delta, we have, and here's my big old epsilon over 3, f of x minus f of c. The way you do this is you add and subtract the same thing. I'm going to go f of x. So I want to use this, this, and this, right? The first one I circled there, the one up top, is about f of x and fn of x. So I go f of x minus, I'm going to use the capital N here. Oops. Subtract fn of x plus fn of x. And now I have fn of x is close to fn of c. So I'm going to go minus fn of c plus fn of c. And then finally, actually that's all I want. I used minus f of c, which was there to begin with. All right, I added and subtracted two things in there. That's for the purpose of what the next step is, to break these up using the triangle inequality. It says f of x minus fn of x plus fn of x minus fn of c plus fn of c minus f of c, and each of these three things is less than epsilon over 3. They are the three circled things that you see up there, all right? So this is epsilon over 3 plus epsilon over 3 plus epsilon over 3, and that, of course, is epsilon, like we wanted. All right. So it's a little long-winded, but what I'm saying, the basic idea is what I wrote on that sort of that diagram. I had these 4 points. They all got to be close together because each of the 3 sides on that little rectangle thing have to be less than epsilon over 3. That's the idea. Any thoughts about that one? This is how to show that if it converges uniformly and each of the functions are continuous, then the thing they converge to is also continuous. All right. Excellent. That's all I got to say about that. There are other theorems of this type. Then I mentioned them last time. It's also true that, for instance, if fn's are all bounded and they converge uniformly, then the thing they converge to uniformly is also bounded. And so on. I said a bunch of those theorems last time. All right. This is all I want to say for now, at least, about sequences of functions. And I'm not sure, depending on how much time we have left, you know, in the whole class, I'm not sure if we're going to get back to this. So this may be the end for this topic here. All right. We had, actually, I'll fill you in a little bit behind the scenes. This point is actually where I had expected to end the class. I wasn't sure if we were going to have enough time, but we have you know, 2 extra days. One day next week I'm going to do review. So just for fun, I thought we could go in and I want to go back and fill in a topic which I skipped over originally, intending to come back to it if we had a couple extra days, and we do have a couple extra days. This is something that I think you'll find quite a bit easier than the stuff we've been doing lately. I hope so, at least. I don't know how you feel about the stuff we've been doing lately, but we talked, of course, much of the semester we spent talking about sequences, but we didn't say anything about series, which usually goes along with sequences. So for our remaining 2.5 days or whatever, I would like to talk a bit about series, if that's all right with everybody, or if not, I'm going to do it anyway. So I want to talk about series. So we're actually going all the way back. I believe this is in chapter 2. There was stuff about series way at the beginning of the book that I skipped past. But we're coming back to it, right? Series. This is something that I think you talked about in your calculus class. So, I mean, I hope the basic idea of it is familiar, and I think a lot of the things that we do will be familiar things you may remember from your youth. But I think we're going to go a little bit farther than you did in your calculus class. That's my hope, at least. So let's talk about series. The word series is not a synonym with sequence. A sequence is, you know, a bunch of numbers. So we're back to talking about numbers now. We're not talking about functions. Although we may, if we have enough time, we'll talk about series of functions, which is an interesting topic. But for now, we're going to stick with numbers. So a sequence, you know, A sub k, is just a bunch of numbers written in a list, right? A series is when you add them all up. When we add them up. Sum of all AK, all right? Sometimes, you know, sort of like for emphasis, this is written as sum k equal 1 to infinity of AK. But usually I'm just going to write the sum because it's a sequence and you're just adding everything in the sequence. Sometimes we want to start partway down the sequence, but usually we're not going to get into that. So a series is when we add them all up, and I write that like with the sum, right? You're adding together infinitely many things. Sometimes this is referred to as infinite series, because they are. Infinite series means you're adding together infinitely many things, and I think it would be worthwhile for us to talk about what does that even mean, adding together infinitely many things. I'm sure you talked about this in your calculus class, but just to make sure we're all on the same page, this is something which requires a definition, in my opinion. So, what does it mean? It involves a limit of something. That shouldn't surprise you. Pretty much everything that has infinities in it really is talking about limits. Not everything, but most things. So here's the true definition of what it means to add together all the terms to get a series. I'm going to define another sequence called SK. SK means you add up the first k terms of the series. All right. Now, even if you don't know what it means to add together infinitely many things, this you definitely do know what that means. That's just adding together finitely many different things. You add them up. And this is the kth partial sum. Partial sum. It's called the partial sum. Obviously, it is a sum of something, and it's partial because it's not the entire infinite series. It's just some of it. It's part of it, right? The first k terms. This is called the partial sum. And those partial sums make a sequence. S1 is just A1. S2 is A1 plus A2, right? S3 is A1 plus A2 plus A3. etc. So SK is a sequence. And what do you get if you take the limit of that sequence? Well, that's what the infinite sum means. So the definition of what the series is, the sum of AK is defined to be the lim of the SK. All right? So if someone asks you, what does it even mean to add together infinitely many things? Your answer is something like, well, you just add together only finitely many things. You keep on doing that, and then you take the limit of whatever that approaches to. All right? The series is defined to be the limit of the partial sums. Any questions about that? I hope this is something that sounds familiar to you. All right. Obviously, because this is a lim here, it means the series might converge or diverge, right? Because it is defined as a limit of something, and we all know that sometimes a limit converges and sometimes it diverges. So the same is true of a series. Sometimes a series will converge, sometimes it will diverge. Here's an example of a series that does converge. I'm going to write these guys in there for this one because sometimes it's more convenient to write starting at 0. Sometimes it's more convenient to write it starting at 1. This series, this one actually does converge. If I were to write out the terms here, 1 over 2, the first term is 1 over 2 to the 0, which would be 1. Then I have 1 over 2 to the 1, which is 1 over 2. Then I have 1 over 2 to the 2, which is 1/4. 1 over 2 to the 3 is 1/8, etc. Anybody know what this converges to? I'm sure you've seen this example before. In your calculus class, you might have even learned a formula for this, although I don't expect you to remember the formula at this point. Check it out. You can try to sort of visualize this geometrically. I'm going to draw this as like a square here. Think about these as areas. Let's say this square has area 1, and then I'm going to try to add onto it a square with area 1/2. Not a square, but just like a rectangle or something. Be the same, but half as wide, right? So this half is like halfway filling up, kind of a. There's like another ghost half that I left out, all right? And then if we add in a rectangle of area 1/4, actually, if you think about it, this 1/4 would fill up half, again, of this remaining ghost half. This would be a 1/4 here, right? And if we add in an 1/8, it will, again, fill in half of the remaining stuff, isn't it? What do you think now? Does this give anybody an idea? What does this all add up to?
2.
2, yeah. Somebody said 2. I agree. Every time you add in one of these terms, you know, that's this one, this one, this one, this one. Each term you add in will fill in half of that empty space. Will never exceed the empty space, right? It'll never go past 2, certainly. And in fact, it will just, if you take this out in the limit, it will exactly fill in that space right there. So in this case, n equals 0 to infinity. 1 over 2 to the n actually equals 2. Now, we're going to talk about how you could actually compute that sort of. I mean, I hope you believe me by looking at the picture, but looking at the picture is not really technical justification of this. We're going to do that in more detail, but that was just one simple example. All right, before we get to that amount of detail, I want to talk about just some very simple rules for series. So our usual limit rules give rules for series. So I'll write this as a theorem. This is the same old theorem that we've seen many times before, the algebraic limit rules. That is, if you add together, like we started off by saying this in terms of sequences. If you add together two sequences, then they converge to like the sum of the two limits, whatever. The same kinds of stuff is true for series. So the theorem says if I have one series, AK, and it adds up to A, and another series, BK, and it adds up to B, then these are like some simple things about how you can combine them together. So the first one I'm going to write is the series of C times AK is equal to C times A for some real number C. If you multiply the series by a real number, it has the effect of multiplying the answer by the same real number. All right. Another way you could write this is the sum of CAK is equal to C times the sum of AK. Of course, that's what the big A means. The big A is the sum of the CK. So really what we have here, this is something like a distributive property, right? It says, because this one over here is C times a bunch of stuff added together. In fact, infinitely many things added together. And the other side says this is all that stuff added together, but with C in front of each term. All right. Really, what that is this is like a distributive property for infinite series. And it is true. The distributive property is true. But really, why this is true is not because it's not true because it's the distributive property. It's true because of rules about limits. All right. Because the ordinary distributive property does not necessarily apply for an infinite sum. Okay, and then next one. This is about adding things together. This says the sum of AK plus BK. If we add all the stuff together inside the sum, it will add up to A plus B. All right, this is another of those limit rules. And this is something like a commutative property because on the right side we have all the A stuff together and then plus all the B stuff together. And on the left side we have some sort of reshuffling of the terms. We group all the A's and the B's together, kind of interlaced. But the limit properties will show you that these are the same. All right. Now there is no rule actually about AK times BK. So this is the end of this theorem. The limit rules included rules about multiplying two sequences together, but I'm just going to say we don't get a rule like sum of AK BK equals A times B. All right, there is no such rule like that. And if you think about this for a moment, you will decide actually there really shouldn't be any rule like that anyway, because this is like what this looks like is A1 plus A2 blah, 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 and then times B1 plus B2. Right? That's what that means. The product of the two series. Whereas the left side would be the series, one series where you stick the A's and the B's together. This would be A1 B1 plus A2 B2 plus etc. And these two things here, they are not the same at all, right? You wouldn't ever think that they're the same unless you don't understand like high school algebra, right? The thing on the right side, if you really wanted to multiply that together, you would have to do a bunch of insane distributing, like FOIL infinitely many times or something. You definitely don't get this on the left side, right? Because, for instance, over here you get something that says A1 times B1, but then you also get A1 times B2 and A1 times B3. Those don't appear on the left side. So there is no rule about multiplying series together, at least not a simple one. There is some kind of infinite infinite foil distributive kind of thing. But even that doesn't always work. So suffice it to say, we're not going to see any rule about multiplying two series together. You don't really get anything that's nice as an answer. All right. Let's talk about a particular simple, maybe simple, I don't know, a particular type of series that you can compute with directly, and it's called the geometric series. The geometric series. This is a fairly common thing in the real world that is easy to compute. By easy, I mean once you know how to do it, it's easy to do it. It's not necessarily something that everybody would come up with on their own, but that's what I mean by easy to compute. It's a common kind of series. Here it is. So for some real number r, the geometric series is this. The sum of powers of r, right? That's called the geometric series, where you have some particular number that you choose, and then you do this to it. You just add together all of its powers. That's called the geometric series. And actually, the one that we did before, and I drew those boxes or whatever, that was an example of a geometric series. So from before, I'll put this in red. From before, I had sum of 1 over 2 to the k, right? K equals 0 to infinity. This, of course, is the same as the sum of 1/2 to the k, right? Just because of how the exponent works. And so this is the geometric series with r equals 1/2. This is a geometric series with r equals 1/2. And we saw, in that case, what you get as the answer is 2. Now 2 is 1 over 1/2. That's a coincidence, though, that you don't get 1 over in general. All right. But anyway, the geometric series is very important in the real world. It comes up a lot of times. It comes up when you're doing like compound interest calculations and lots more stuff. We got 15 minutes left. That's enough to talk about how do you actually compute the geometric series. You know, I drew those boxes and we could see that that one added up to 2, but really we want a better method than drawing the boxes. And actually there's a deeper question that we can ask is like right here. So when r equals 1/2, it converges to 2, right? The answer is 2. But it would be nice to know which r's does it actually converge. So for which r does it converge? For which values of r does it actually add up to some finite amount? Versus if the r is, I suppose, you should feel like if the r is too big, then it's not going to converge to anything. It'll just like sort of add up to infinity or something. For example, if r equals 1, then what does it look like? It looks like sum k equals 0 to infinity, 1 to the k. But of course, 1 to the k is just equal to 1. This is the sum of 1. And what that means is 1 plus 1 plus 1 plus 1, etc. And that diverges, doesn't it? This does not add up to a particular number. It doesn't, if I look at the partial sums here, they don't have a limit. They don't approach any particular number. They just go up to infinity. So this one diverges. So apparently if r equals 1, the geometric series diverges. The question I'm trying to ask here is for which r's does it converge? Well, we'll see. There's a sort of a trick for computing the geometric series. To compute it, we get the sum of r to the k equals 0 to infinity. What can we do with that? Well, this, of course, is defined to be the limit of the partial sums, sk. Can I write down what sk looks like? It looks like 1 plus r squared plus r to the k, right? This is the partial sum, taking only k things, adding them up. You start with the first thing, which is r to the power 0, then you get r to the 1, and so on, up to r to the k. All right. And here's the trick to compute what I really want to find the limit of sk. The problem is this is not convenient to find the limit because of this dot 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 here. You can't really take the limit of a dot dot dot. So what I want to do is a simple trick, and this is not something you might think of, but once you see it, it's you can work it out. I'm going to multiply both sides by 1 minus r. So on the left, we get sk times 1 minus r. And on the right, we get 1 minus r times 1 plus r squared, r to the k. All right, and this we can simplify. I'm going to leave it like it is on the left side, but on the right side, I'm going to actually multiply that out. You got to do a big sort of FOIL thing, distributing 1 minus r across the entire thing on the right. So first let's multiply the 1 onto everything, right? Like this. I just drew an extra little thing here. So anyway, I get 1 plus r squared plus r to the k. I just multiplied everything times r. And then I subtract and I multiply everything. Sorry, what I just did so far, I multiplied everything by 1. Then I go through again, multiplying everything by minus r. What I get is, from the first term, 1 times minus r is minus r. Then I get minus r times r, which is minus r squared. Then I get minus r times r squared, which is minus r cubed, etc. The very last one, minus r to the k plus 1, right? Why'd I put parentheses there? There's no parentheses. I multiplied through everything by negative r. And the last one ended up being negative r to the k plus 1. What do you say? Can I simplify in there? I think I can. Anybody still with us? I think you can cancel a bunch of stuff. What do you end up with?
1 minus r to the k plus 1.
Yeah, all the stuff that you see on the inside here will cancel. This r cancels this minus r. This r squared cancels this r squared. This r to the k actually cancels a negative r to the k, which you don't see, but it's in there, right? All of those will cancel except 1 minus r to the k plus 1, all right? And now, each of these things are equal to sk 1 minus r, right? And now I can solve again for sk. It is 1 minus r to the k plus 1 over 1 minus r, like that. All right, and this is a much more convenient form for sk, and in particular we can use this to take the limit. So now the series r to the k, of course it is the lim of sk, but this is going to be lim of 1 minus r to the k plus 1 over 1 minus r, right? And I'm taking the lim in terms of k. So actually everything that doesn't involve a k here can get kind of factored out of the limit. This is the same as 1 minus lim r to the k plus 1 divided by 1 minus r, right? The only part of that formula that has a k in it is that r to the k plus 1. And I take the limit of the whole thing. It's the same by the limit rules about adding and multiplying limits. It's the same as this limit here. And then what is lim of r to the k plus 1? You got to imagine you're just looking at a particular number and taking powers of that same number. and taking the limit of those things. That limit is either going to be 0 or the limit diverges. So lim r to the k plus 1 is either 0 or it diverges. Like if r is a half, the limit is 0, because if you take a half and you just like keep multiplying it by itself over and over again, the limit of that will be 0. Whereas if r is something like 3, if you take powers of 3, multiply 3 by itself over and over again, that diverges. It goes to infinity. So can we say, when does this equal 0? So it is 0 when, can you say something specific about r here? Certainly, like when r is a half, this limit is 0. What in general do you need to be true to get 0 in this limit? Remember, this is the limit that happens when you multiply r by itself over and over again. In what case will you get 0?
R is between 0 and 1.
Yeah, she said when r is between 0 and 1. Now, you mean between like the open interval?
Well, it can include 1. I don't know if it can include 0.
Yeah, you cannot include 1 here. Is it true if you have 0 and multiply 0 by itself over and over again? I think that gives you 0, right? So this actually is 0 when, can I say when r is less than 1? Right? And it diverges when r equals 1 or r is greater than 1. Diverges when r is greater than 1. I have just one thing to, greater than or equal to 1, right? I have just one thing to add here. I think whoever said that answer was only thinking of r being positive, but if let's think, what if r is negative? Well, it's sort of the same thing, but if r is like a really big negative number, then this sequence will diverge. If it's a less than 1, it's negative, but with like a fraction, then it'll go to 0. So the simple way to fix that up is just this. Put some absolute values around them, all right? When the absolute value of r is less than 1, then you get 0 in the limit. And when the absolute value of r is bigger than 1, it diverges. All right, so I was just talking about this little part right here. So the true answer to what is the value of the series, let me just write it as a theorem. We just did the proof, but it says the sum of r to the k is, well, it diverges when absolute value r is greater than or equal to 1, and if absolute value r is less than 1, then the sum r to the k equals, it's this, what we said before. It's going to be this, but that lim part is going to be 0, like we said down here. So it's this, but just put 0 instead of that lim part. It's just 1 over 1 minus r. A very nice and easy, simple formula for the geometric series, right? And so in particular, like for that that example that we did at the very beginning, sum of 1 over 2 to the k, right? K equals 0 to infinity. This, of course, is the same as the sum of 1/2 to the k, and that is 1 over 1 minus a half, because I use the formula for the geometric series when the r is a half. And then what is that? You can simplify that. 1 minus a half on the bottom is a half. 1 over a half is 2, which is, that's the answer we got last time. But this is the real sort of proof that the answer really is 2, rather than just drawing the little, the look at those boxes proof. All right. All right. This is the geometric series. Important real-world phenomena obey geometric series. And lucky for us in the real world, it's easy to find the limit of a geometric series. Or it's easy to find what it converges to. All right. We got 5 minutes left, but I think maybe we can leave it at that. Next time we will do a little bit more concerning series. All right. I hope you all have a good weekend. See you next time.